Hello, everyone, and welcome to the new episode. In this episode, I'll be talking about entity embeddings for categorical variables. And before I begin, I would like to ask you to like, subscribe, and share my videos if you like them, and it motivates me to keep making new videos. So, in the previous episode, one of the previous episodes, which was about categorical features, we learned a few different ways of dealing with categorical variables. So, what were those different ways? Let's look at them. So, the different ways of dealing with categorical variables included. Yeah, that's way too big. Okay, let's select this one. So that included binarization, in which we binarize the categorical features. The second method was label encoding. So this is binarization, so it can be 001, 010, 011, and so on. Label encoding, in which we represent each value by a number. And then we had one-hot encoding. So if you have three features, it will be 001, 010, three categories, and 100, so like this. So the new method that we are going to talk about today is dealing this categorical variables from more of a model perspective rather than pre-processing. So as you can see, I have this paper in the background, very cool paper, which discusses entity embeddings of categorical variables, and it shows how categories are mapped into Euclidean spaces, which are the entity embeddings of categorical variables. And this paper actually comes from a Kaggle competition, so they got third place. I think it was Rossmann, and I'm not sure. You need to check that out. Probably it was Rossmann. So it shows that with much simpler features, you can beat many benchmarks using entity embeddings, and that's something that you should go for. So what do we have is we have, in the world of natural language processing, let's say we have a word like Norway, and this word is represented by a vector, right? So that's the embeddings for in the natural language processing world, and this vector can be of dimensions 100, 300, depends on what kind of embeddings, and they are fast text. Usually people use fast text, glove embeddings, and so on. Word-to-vec, right? So for categorical embeddings, let's say you have a dataset with many different features, and C1, C2, C3, C4, and let's say a target. So all these features, starting with C, are categorical features. So these are categorical features, and our plan is to create an embedding representing the features inside. So let's say C1 has 50 different values, right? So what you do when you take one-hot encoding is you create a vector of size 50, and then you fill in the values. Like this is 1, rest are zeros, right? Only one value is 1. And categorical entity embeddings work in a very similar manner. So instead of creating a vector of size 50, because if you create a vector of size 50 for 50 different categories, it's just going to be one hot encoding. You can create a vector of size 10, right? And then this will have some values. So one of the categories inside C1 feature that we have will be represented like this. So now, since you have 4 different categories, C1, C2, C3, C4, you choose how many, what kind of dimension of the embedding do you want. Let's say we want 10 for C1, and it had originally 50 different categories. C2, we have 3 different categories. So let's say we choose 3, one hot encoding. C3 has 1000. C3 has, let's say, 1000 different categories, different values, and we will choose a vector of size 128. We can also choose 64. Depends on you. You have to try different values and see what fits. And similarly, we have 10,000 different values. So I can choose a much larger vector, let's say 256, 128. Okay, so now we have created embeddings for all these different. We have chosen like the dimension of embeddings, and now we have to learn them. So we can learn them by using a neural network. So we have embedding 1, embedding 2, 3, 4. Let's say these are the 4 different categories, and these are my embeddings. So they go inside a neural network. So what we do is we apply some kind of dropout if we want to, and then we flatten them or reshape them. So what happens after that? This one becomes something like this. So let's say this was 10, 3, 64 and 128. So this becomes something like this. So you have size 10, then you have 3, 64 and 128, and you concatenate them into a large vector, right? And then you apply a dense layer, and you can apply dropout, batch normalization, and then you can apply a bunch of these if you want, and then target. Right, so that will be 0 or 1, or depending on if it's a regression problem, then it can be different. So that's basically it about categorical features, using entity embeddings for categorical features. You have created an embedding, so this embedding learns, okay, if you have different categories, let's say days of the week, Monday, Tuesday, Wednesday. So you can if you put in 7 different categories here, if your dimension is 7, then it's going to be one hot encoding. If it's less than that, then it's going to learn something new. And Similarly, if you have many different categories, you can reduce the number of you can reduce size of the embedding. So if you have tens of thousands of categories, probably you just want to learn embeddings which are only of the size of 128, let's say. So that reduces a lot of memory constraints that we have. And also this kind of model, since it's neural networks, you can keep on updating it with new data. As you get new data, you can keep on updating it. And it can also handle rare values quite well. So if you have rare values, put them into a new category called rare, and then your embeddings can be learned for those rare values. So we see that with much simpler features, we can beat many benchmarks using these entity embeddings, and it also allows us to handle many different kinds of categorical features, and also categorical features with very high cardinality. So enough talking about how it looks. Let's go and try to implement them now. So to start with coding, first of all, we need some data, and this is an ongoing challenge, playground competition going on, and we have already seen the data for this in the categorical features main episode. So you can see that all the columns here are different categories. So what we are going to do is we are just going to use this data here, and let's try starting a new kernel. We need GPU. Create. Okay. So now it's starting the new kernel. So the first thing that we would need is to import some useful libraries that we always need. Just going to remove all the stuff. Okay, so yeah, I don't know if we need OS. Let's keep it for now. And then we load the training and test datasets. So train is my pd.read CSV. I hope this is visible. Just make it a little bit bigger just in case. pd.read CSV, and then that's in my input. Cat and the dat2 and train.csv. So that's my training set, and test, and the sample submission sample.csv. Okay, there we go. Call it sample. And now we have that. We also see that when you do train.head, you see like there are many variables which are not just numbers but strings. And since it's categories, so we can treat everything as strings. So what we do is we will encode them using label encoder. So from sklearn import pre-processing. Okay. So I will add a new target for test. So test.log target. So this is a fake target. This is -1. It's just because I want to combine training and test set together. Now why I'm doing that is because there are a lot of new categories in test set which are not in training set. You should not do that. You should rather use rare value if you want. But here I'm using some kind of let's say semi-supervised learning. And my data will be pd.concat training test, and I will just reset index drop true. So it's going to reset the index. So now what do we have? We have data.shape, which is 1 million samples. So your data.shape train. Okay, so 600,000 training samples and 400,000 test samples. So that's a lot of data. So now we have to choose features. So features will be train.columns, let's say, but we have to choose only those columns which are not ID columns and not target columns. So I will say F for F in train.columns. If F not in ID comma target. So these are the columns that I want to use. So now if you see features, you have all the different types of features excluding ID and target. Now we need to label encode them, so convert all these to numbers. So I can just do for feet in features say label encoder is, we have already imported pre-processing from scikit-learn label encoder, and then we say data dot lock feet is equal to label encoder dot fit underscore transform. So I'm just fitting it and transforming everything at once. So if you want to use it, reuse it, then you should use the same way we implemented it ML framework. Fit underscore transform data features dot, I'm just going to say as type str, convert everything to string dot fill na with -1. Okay, and then we have I think that's it, right? Fill na -1 dot values. So this is going to transform each and every feature. So let's run it, and then it's going to probably take a little bit of time because there are many features. Okay, so now we can see data.head. So now everything you see has been converted to numbers. There were also NaN values, but we filled them with -1. And now we are good to go. So we can go for categorical encoding. No, sorry, entity embeddings for these categories. Also categorical encoding. So now we have train dataset and test dataset, and we join them together. So let's get them back. So we can do training set is data dot target, which is not equal to -1 because this is the value we filled. Set index, we don't need the old index anymore. And then we have test data, which is -1. Okay, so now a very interesting thing that I'm going to do is to convert all these features into list of features. Lists of features. Let's see. So my train.shape, I can just verify it again, and test.shape. It's 600,000 and 400,000. Now what we have to do is to create the model itself. So before creating the model, because we will be supplying it with something so let's see. Okay, let's say I define GetModel a function, and for this specific video I'm using TensorFlow keras. So let's import some of the stuff from there. Import TensorFlow as TF, and then some more things from TF keras we need. So from TensorFlow.keras import layers. Can do optimizers. From TensorFlow.keras import. Do we need anything else? We probably need keras.models, import model, and load model. Load model for later. It's only model. I think we don't need load model for this video. So I hope we have everything now. And we create a GetModel function which takes a data frame df and categorical columns, two different inputs, and then we define two lists, inputs and outputs, right? And we say for C in categorical columns, we find out what are the number of unique values for a given category. So here df is my training set. Let's say categorical columns are all those columns that we printed here, so all of these, and then we try to find what are the number of unique values. So number of unique values will be just int of data c dot values. We are using df c dot values, and then you decide what is the dimension of the embeddings that you want for this specific column. So embedding will be, so I will explain this. Okay, so this looks good. So this is like I'm taking ceiling of number of unique values divided by 2. So if my number of unique values is 100, it's giving me 50, min of those two. Well, my unique values is 35, then my embedding them is 18. So it totally depends on you how you want to do it. So if you have a lot of different types of different, if your cardinality is very high, then you probably need more than 50. Otherwise it's it's quite okay to use this. So now we have one input, and that will be layers dot input, and shape of this will be 1, comma. That's it. And output will be layers dot embedding num unique values, the number of unique values, plus 1, always one more than that for embedding layer, and embedding. And you can also specify some name for this if you want. So I will say name is C and input. Okay, and now output will be I'm not going to apply any kind of dropout here, so I'm just going to reshape it to, so it can be reshaped to its dimension of embeddings. And target shape is wedge dim, comma, and this takes output. Okay, so now you append to inputs and outputs. So inputs dot append inp and outputs dot append output. So now if you want to apply any kind of dropout, you have to do it after this line. So you need to apply dropout here, apply dropout here, and it's always a good idea to apply dropout, introduce some kind of regularization. So once you have gone through all the categorical variables, now what you can do is you can concatenate them into one single feature vector. So I will say start with something like x is layers dot concatenate and concatenate all the outputs. Fine. After this, I will add a dense layer, layers dot dense of dimension, let's say 300. This is also up to you. Activation value and x. So I've added one dense layer, and I will also add a dropout layer 0.3 x. Okay, so this is your model now, but you also need the output. So this is a binary classification problem. I should have specified that earlier. So this will be layers dot dense, and we will just have two different classes or one different class. You can also use the sigmoid or softmax, whatever you want. So let's use one and activation sigmoid. Right, this takes x. Now you compile, now you get the model. So model inputs is your inputs, which is a list, and outputs is equal to y, and return model. Okay, so now this function is going to return me the neural network. So let's see, get model, and I can say train and features. That should work. No, it doesn't work. So what is it? Train features. Only size 1 arrays can be converted to Python scalars. Of course. So this will be and unique. Okay, let's see now. Okay, so yeah, so it gives me the model. So let me print the summary. Great. So we have the model, different inputs, and you can see all inputs have the same shape, which is not desirable. So okay, just so you have different inputs, that's fine. And then you have these categorical features. So you can see these have only 2, the dimension of embeddings is only 2, and then it's 4, then for these it's 50, 2, 3, blah blah blah. Anyways, after that we reshape everything and then we concatenate, so we end up with 369 features. And then we apply a dense layer, a dropout layer, and a dense layer with a sigmoid output. So we have total of 390,000 parameters trained, and that's quite good. And it was quite simple to implement this model. So now we can start with the actual training process. So how do we do that? It's actually also very easy to do it. So I will say my model is GetModel. I've already done that, train comma features, right? And then I have to compile the model. So model.compile, and loss equals to binary cross entropy, and optimizer Adam. Let's see, and then model.fit. So now you have one target value and different features. So how to get the different features? It's actually quite easy to format the input. So what you can do is you can create a list and then write train dot lock comma features train dot lock this comma f dot values, right? For f in features. Okay, so if you run this, it's going to give you a list of list. I'm not sure if I should run this. Okay, let's try. I'm just going to do train.head 100. So now you see it's a list of features from each column. So list of lists or list of arrays, and then here you have train dot target dot values. Let's see if this works. Yeah, okay, so you can see we are able to train good, and now we can also do the predictions. So it's going to take a while for this to train. It's a lot of data. You can actually increase the batch size a little bit, and then you do model.predict to generate the predictions for test dataset, and then you're done. So yeah, quite easy and simple way. I have already created a model for this specific competition, and I've shared it a while ago, so you can take a look at that. Let's same old entity embeddings. So you can take a look at that, and this gives a quite good score actually. And I didn't invest much time in improving that, so you can do that. One task would be to convert this model to PyTorch model, and then once you're done with that, make the kernel public and share it in the comment section for everyone to see. So that's gonna be a quite interesting task, and I think it's pretty easy. It's pretty easy to do that. And I think that's it for today with the entity embeddings. So I will not wait for this to end. I have already shown you like the score is quite high anyways. So if you like the video, please press the like button and subscribe, and share it with your friends. And there are a lot of new different things in the pipeline. I'm still working on some regression and advanced metric, so that will be in the next episodes. I'm also going to show you how to serve the sentiment model that we trained using Docker. So that's also going to be quite interesting. And if you have any ideas about the videos, feel free to send me a message on Twitter or write in the comments, and let me know how was it, and if there's anything that I can improve. And thank you very much. See you next time. Bye.